Dr. Kyle Thompson is a research scientist within the Aerothermodynamics branch at NASA Langley Research Center. Dr. Thompson develops and maintains the LoRa and Hypersolve CFD codes, and his research focuses on novel and robust techniques for simulating hypersonic flows encountered in NASA entry, descent, and landing applications.
Thanks for the introduction. Yeah, this talk is on basically faster answers for steady state simulations using CFD codes, particularly when we have strong shocks present. So I'd like to acknowledge my co-authors who are instrumental in making this happen. That's Matt O'Connell and Cameron Dreyer at NASA Langley Research Center. And the motivation for this talk and presentation comes from not only the fact that I think everybody would like faster CFD solutions, but specifically it was called out in the CFD 2030 vision study that what is required for the future is an automated capability that delivers hands-off, solid convergence under all reasonable anticipated flow conditions with a high tolerance to mesh irregularities and small-scale unsteadiness. And we've made a lot of progress in the field of CFD over the last 20 years towards improving our nonlinear solver technology to make it more robust. That includes things like multi-grid methods, constraint-based solver techniques, such as the work by Marco Sezzi, and then the focus of this particular talk is on Newton-Krylov techniques, which have kind of come back into fashion recently as we've gotten to the point in HPC where we can run very, very large problems with a lot of memory and a lot of cores. And the reason these Newton-Krylov solvers are so attractive recently is that they can really accelerate your iterative convergence if you've got a good starting initial condition. So the Newton method gives a nice quadratic convergence rate compared to other techniques that would be either linear or superlinear. But they kind of come at a cost where they can stagnate when you've got strong nonlinearity present in the flow field. And one particular nonlinearity that is very, very common in the field of hypersonic flow is strong shocks. This can lead to a lot of waste early on in the simulation when you're spending a lot of these nonlinear iterations just moving the shock around. And so that's the problem, is that when you're doing a Newton-Krylov solver, you can get very fast convergence, but each one of those iterations that you're spending are much more expensive compared to other techniques because you're solving an ill-conditioned linear system that's usually very expensive to construct and robustly solve. And if you can, get to the point in your where you're getting that quadratic convergence rate quickly, this isn't a problem that they're so expensive because you're not spending a lot of time on these iterations, or you don't have a lot of iterations where you're spending this much time. But if you can't do that, then your efficiency is going to deteriorate very rapidly. And so you have to use some kind of globalization strategy for these Newton-Krylov methods. And there are a lot of techniques out in the literature on this. So the common ones are things like pseudo-transient continuation, also known as local time stepping or dual time stepping, line search methods, and trust region methods. And they are all some form of what we call hill climbing methods, where if you've got some kind of local minimum that you need to walk yourself out of, they can help with that. But typically they all fail to improve the efficiency of Newton-Krylov significantly when shocks are present. And getting to shock specifically, got an animation here which shows that if you start this flow of a cylinder in hypersonic conditions, the shock kind of violently lifts off the surface and takes a really long time to reach the steady state position. So this is a really simple example of a simple case where the Newton-Krylov method really starts to struggle. And we need some kind of method to kind of help us walk that shock all the way from the surface out to its final case. And you'll see here up on the right, I've got a plot of just how many iterations it took. It took over 250 iterations for this simple case to get converged. And once you get through those, I think probably about the first 230, you get that nice fast quadratic convergence, but you spend all your time basically at the front wasting time with this shock moving across your domain. And so basically what you see is that all progress is stymied by the shock until it gets into that final location, but it's really just held up by a small region. So this is a known problem, and there's a number of solutions out there. One in particular is what's called nonlinear preconditioning, and it's this idea that we know that the failure of Newton-Krylov solvers is due to the unbalanced nonlinearities in the domain, and we need some kind of preconditioner at the nonlinear level to mitigate these unbalanced nonlinearities. And one technique is nonlinear elimination. So if you look over on the right, I've got a kind of an image of that cylinder problem where if you look at the flux balance at every point as a 3D contour plot, you can see that your shock has a really, really strong imbalance, but everywhere else, it's relatively smooth and even. And so this nonlinear elimination technique exploits that observation. It's developed by Kai and Lee, where you effectively fix that problem by partitioning the region where you've got that strong nonlinearity, in this case the shock, and you solve it as a local subproblem. And the idea is that you now have a smaller, better conditioned subproblem that's going to give you a better starting condition for the global ill-conditioned problem after you solve that subdomain. And so the first thing to achieve nonlinear elimination is to identify where that nonlinearity is. And so we need some kind of shock sensor. And the work that I'm presenting here, we're using a combination of the shock sensor by Lovely and Hames and Notho and White, where we basically use the dot product of the Mach number, directional Mach number, and the pressure gradient. And then we filter it out based on a pressure-based sensor for that. And in practice, the value phi here, any value greater than about 0.1 indicates that we have a shock. So if you look here, when you apply that shock sensor, you get a pretty clean picture of where that shock region lives. After you've identified the shock, the next step for nonlinear elimination is to build a subdomain and then solve it. So I've got a diagram in the left here that shows a region in red where that shock was detected. And then we've got two more regions kind of adjacent to it that are in green and blue. These are what we call the overlap region, where you're going to extend the subdomain out by walking over edges until you get a certain amount of overlap. In this case, it's an overlap of 2. And you're going to then, at the very edge of that domain, fix the solution. Once you've solved the entire region that's not in gray, everything that's in gray has been discarded, you're going to solve that region, and then you're going to only inject the solution from the red region where that shock was back into the global domain. And then on the right here, you can see that before the subsolve, you've got all that interesting nonlinearity, and then by the end of it, everything's much smoother and flatter. That helps with that global problem to solve. And so this is what we call restricting the solution. And the more overlap that you add to the domain, the more work you have to do, but also you've pushed kind of that boundary region where you're generally going to have the most effect of the global problem not matching up with the subdomain kind of farther away from that. So there's a trade-off there about how much overlap you should use for this, and it's a little bit case dependent. So I'm going to show a bit of results here using one particular CFD code called Hypersolve. So Hypersolve was developed in NASA Langley Research Center. It's an edge-based unstructured finite volume CFD solver that uses dynamic load balancing for both the global domain and that shock detected subdomain that I just described. And it's based on a lot of the work that was presented back in 2019 by myself and Matt O'Connell using a library called Enigma that wraps the PETSI library. And we use the Jacobian free Newton-Krylov based on that library. For the linear solver and the JFNK solver, we're using the same algorithm both on the global and the subdomain for the solving, which is we use an additive Schwartz preconditioner, where each partition in the Schwartz preconditioner is just using ILU with 0 fill. That's a right preconditioning of the GemRes solver, which uses 50 Krylov search directions, and we do not restart. So after 50 search directions, we terminate the linear solve. And then we also supplement that with an additional globalization strategy where we're doing local time stepping, as well as a backtracking line search for stability. So the first case, I've got 4 cases to show here using nonlinear preconditioning and its effect, is that cylinder case. It's basically a 2-dimensional quad mesh. And the flow conditions in this particular problem are 5 kilometers per second flow with a wall temperature that's a constant isothermal wall of 500 Kelvin. And for the subdomain, I mentioned that there are some parameters that you have that you can use to tune that subdomain solve. The first is what tolerance you want the flux balance, the L2 error of the flux balance to decrease by. In this case, we just seek about a 10% reduction in the subdomain solver. And we're doing that subdomain solve with a frequency of 1. So every single iteration, we're doing a subdomain solve before we do another global solve. So we solve, inject the solution, solve, inject the solution, and so on and so forth. The overlap region is 2, and then the max number of iterations for each subsolve is capped at 10. So if we haven't reached that relative tolerance after 10 iterations, then we terminate that subsolve and take whatever we got from it. And this worked pretty well. So we got about a 22% improvement in overall wall time using nonlinear elimination with our Jacobian free Newton-Krylov solver and Hypersolve. And you'll notice that once you've hit that quadratic convergence point, you really don't see that big a difference in the convergence rate. So that just kind of goes to show that it really does a great job at moving that shock out, which gives you that 22% improvement. But once you've hit that, you can probably just stop doing the subsolve and turn it over to the just standard JF&K solver. The next case here is the exact same flow conditions with the same subsolver settings, but it's also with a triangular mesh instead of a quad mesh. And in this particular case, we see a 38% improvement in overall wall time. And so the theory for why this is so much more, it's almost twice as much improvement, is the fact that the previous quad mesh was shock aligned and this one's not. And so you're seeing the effect of increased dissipation due to the shock misalignment. The third case of the 4 cases is a 3D case. This is on a hemisphere. The flow conditions for this one were a little bit more benign. This is a 1 kilometer per second flow. And we did have to change the subdomain solver settings to only solve the subdomain every 5 global iterations. And with that, we saw about a 20% improvement in the overall time to solution. The reason that we think increasing the frequency for this one just comes from the fact that if you've got something that's well shock aligned and you're moving that problem out in 3D, if you're not effectively solving that subdomain, doing it every single iteration is not really helping you. And so there's probably some optimal tuning that we need to look into with this method to kind of automate how often we need to subsolve these 3D problems. But we do still see an improvement with this. And if you set that subsolve frequency, I don't show it here, to 1, you still improve slightly, but I would say it's like a 2% improvement versus a 20% improvement. And then the last case that I'm going to show here is the same problem as the hex mesh on the hemisphere, except it's a tetrahedral mesh, and we see about a 25% improvement. And with this, we're able to go back to a subsolve frequency of every iteration. And the reason that this seems to work is for the same reason we think that the triangular mesh worked better than the quad mesh for the cylinder, and the fact that it's not shock aligned. So the nonlinear elimination technique seems to work, be more effective when you've got these truly unstructured simplex meshes that aren't necessarily completely well shock aligned like you would get from these structured meshes. This is my last slide, so just to wrap everything up, in summary, the nonlinear elimination technique can be effectively used to decrease the time to solution when you're doing these Newton-Krylov solvers with shocks. The key ingredients to making this all work are a shock sensor, dynamic load balancing, and then having some mechanism for being able to solve these subdomains and transfer the solution from them. And it provides a very nice mechanism for being able to balance the total nonlinearity of the problem, especially when you've got things in regions where the nonlinearity is extremely imbalanced due to something like shocks or maybe even shear layers. The efficacy of this is dependent on the relative imbalance of the localized nonlinearity. So I'll just point out that it's known in the literature that when your problem is globally bad, that these subdomain solver techniques are not cost effective. Fortunately for bow shocks, this is not true. You're almost always going to have a very highly localized phenomenon where these subsolvers can be very effective. And then as I pointed out, there are some tunable parameters in these. And so future work will seek to optimize these parameters so that it's not up to the user to pick the optimal frequency of the subsolves or the relative tolerance of the subsolve. And with that, thank you for your attention. And I will take any questions.
Thank you very much. Very good, very interesting work there, Kyle. We have one question from Michael Elmore. Is this only appropriate for steady state cases, or can it maintain time accuracy?
It's applicable for both. Steady state is the primary use case, but if you're doing any sort of time accurate method that's an implicit step process, such as like a backwards difference Euler, the subsolver technique will still help you. You just may not necessarily need it when you're doing those sub-iterations. It may not be as cost effective for that. So I would say it's applicable to both, and it will maintain time accuracy for both when you do that, since it's just injecting the solution into the global domain. But it is much more of a target for steady state problems.
All right, very good. I think we have time for another question here. This is from William Klebb. In the context of a solution adaptive mesh adaptation, is subsolve still necessary effective for meshes past the first?
Yes, and that was the reason that I showed some of the examples that were both structured versus unstructured. When you're doing these adaptive mesh, when you're doing mesh adaptation, particularly with unstructured meshes, and if you're hopefully interpolating the solution from a previous adapted mesh onto the newly adapted mesh, these subsolves become much more effective. And the reason for that being effective is usually that your shocks, when you do the interpolation, if that interpolation isn't conservative, your shock is going to be imbalanced. That shock speed will be slightly wrong. And so being able to do this procedure is very effective for that. In practice, what we find is that you typically only need to do one or two subsolves towards the beginning for these adapted cases, because that solution is so close to where the Newton solver starts to converge quadratically. You don't have to kill it like I did here, where you're solving it every iteration. But it is effective past the first mesh for sure.